Okay, in this video, we're going to look at the actual tool paths to machine out the gearbox plate here on the fixture plate. Just a quick recap of where we were from the previous videos. We talked about how we need to hold down a piece of stock material to the fixture plate with some screws. These screws thread into the fixture plate, and so we have to have holes in the stock material that match up with the fixture plate. And so in the previous videos, we talked about how to do that. And now that we have that, we want to actually set up the tool paths for the actual gearbox plate. So I am hiding the stock material. I'm also hiding the screws for now. And I took some pictures of a similar process. These were for different parts, but here's the picture of a fixture plate here. You can see that it is mounted to the mill, and I clamped down a piece of stock material to the actual fixture plate. This stock material was smaller than the fixture plate, so I just kind of held it just at the edges. If the stock material were larger, like the entire size of the fixture plate, you'd have to use different clamps that were bolted into the side or the T-slots of the mill. But since this was a little bit smaller, I didn't need to do that. I just needed to hold it down enough so that the holes could be bored into the stock material, and then I could thread through the stock material into the fixture plate. And so that's what the previous videos had covered. And then once that is done, then we have screws holding down the stock material flat on the fixture plate. And then the final process would be then machining the parts out. And so these parts were machined out. And these holes here, these larger holes in those parts were bearing holes. And so holding that plate down flat on the fixture plate helped ensure that they remained round when we machined them and after the parts were taken off. And so back to this situation. So now I'm going to hit the cam tab, and you can see we have setup one, which was the tool paths to actually bore those holes that match up with holes in the fixture plate. Now we're going to just create a new setup for the actual tool paths to machine out the gearbox. However, we're going to keep the same work coordinate system and everything. So the easiest way to do that is just right click and duplicate. And I will call this setup 2. And this setup will be the setup that contains the G code for the actual plate. So I'm going to delete the bore operation there. Also, if you notice this check mark means that setup 1 is the default one. And so if I create a new toolpath, it will go up to setup 1. I want it to go to setup 2 here. So if I right click and go down to default folder, it puts the check mark by setup 2. So now any new tool paths will go in this setup. So looking at this gearbox, if we do an inspect and we take a look at these little weight reduced pockets, they don't go all the way through. And the plate itself is a 1/4 inch thick, but if I measure from here to here, we can see that that's 0.188 or close to 3/16. So basically that leaves 1/16 of an inch remaining on the bottom of the plate. Now these pockets aren't really pockets, they're actually counter bores, and they're not as deep. They're 1/8 of an inch. These counter bores, notice, have a small hole through the middle, and then this larger counter bore, and these are actually meant for standoffs between two gearbox plates. So those are at a different depth than these. Then we have a couple of bearing holes. We have, of course, the through holes on each where the counter bores are. And then we actually have some tapped holes here. We're not going to be doing any tapping on the fixture plate because we don't want to go we don't want to tap into the fixture plate, and a tap actually has to extend through the actual plate to get the threads all the way through. So we'll get the holes made, and then we will just tap that by hand. There is a way to thread mill those holes on the mill, but that is for a more advanced class, and so we won't cover that. So in this situation here, let's go to the cam tab. We're going to do some adaptive clearing of these pockets here. So I'm going to go to the adaptive, and I'm going to try something different. If you remember, usually we've selected the top part when we did some tubing. I'm going to actually select the bottom contour on these. And to save a little time, I'm just going to do, let's do these 3 or these 4. We'll do these 2 counterbores and then these 2 pockets right here. Notice that I selected the bottom, and these are at different heights or different depths here. Let's start with a 1/4 inch end mill, and let's do the stub end mill. Again, I prefer the stub length end mill to the regular end mill if we can use it, because there's less deflection when machining, and so it can machine more quickly. And then we already selected the geometry. Notice the depth by default is the selected contours, and that's really nice because I selected at the bottom, and so I don't have to do anything for the depth, and it will machine at the correct depth because I selected the bottom of those contours, which is the bottom of the pocket or the counterbores. Going to the next pass, I want to make sure I don't leave any axial stock because I just basically want to be down at that depth. But I am going to leave a little radial stock, and then we'll come back with a contour to clean that up. And again, the radial is around the edge. Okay, so let's just hit OK and see what happens here. Notice that these look great. We have the helical entry, cleaned out that counterbore, helical entry, cleaned out that pocket, but it skipped these 2. And really the reason is these are pretty small, and the helix that we set is too large for these pockets. And so the default helix diameter is set here on the last tab, which is the linking parameters. And you can see that the ramp diameter is 0.23. If we go to something smaller like 0.2, you can see that we actually get this pocket, but we don't get this counterbore. We can keep going smaller and smaller. The problem is if you go too small with the helix, the machine is really accelerating a lot trying to make this tiny helix. And so I really try to avoid that. And since this is so small, I recommend we just use a different tool, a smaller end mill to do that. Now you might say, why not use a smaller end mill for everything? And the answer would be, it'd take a really long time to machine everything out if we use such a small end mill. So let's wait on the smaller counterbores. There's 4 of them here, and use a smaller end mill. So what I'm going to do is go back to the geometry. Let's undo this so I can, if I hit Control and click, it deselects that. And let's go to all of the remaining pockets here, or the 2 large counterbores. Okay. Making sure to select the bottom there on each. So now that we've selected those, we can hit OK. And we want to check to make sure that we've cleaned everything out. That looks great. Everyone is being cleaned out. Now we need to follow this up with a contour because we've had that radial stock to leave. And the easy way to do that is right-click, go to Create Derived Operation, and go to 2D Milling, 2D Contour. Creating a derived operation keeps the same tool, the same geometry, the same depth. And notice there is, by default on the contour, no stock to leave. So all I have to do is hit OK, and that is done. So we basically cleaned out the material, and we've done the contour. Looking at the simulation really quick, you can see that the tool is going down and doing the adaptive. I'll do this quickly. Then when the adaptive is done, we jump to the actual contour that takes off that extra amount along the perimeter to leave a nice finish there. Okay, now the next thing we want to do is look at these small counterbores. These counterbores are really the same process, but we need to use a smaller tool. Let's jump down to a 3/16 inch end mill. That's the next smaller tool we have in our library. So let's go to 2D Adaptive. Select these here. On the tool, we're going to just go to the large machine that we have. The 3/16 inch end mill is the next smaller one. Has a diameter of 0.1875, just 3/16. And so then we can set the depth to be selected contours, which is what we did. We selected the bottom of those counterbores, take off the axial stock to leave, and see if that works. Still doesn't work, so we need to go to a smaller helix. And so let's try a little bit smaller. Maybe we can go 0.15 and see what happens there. You can actually do the math to figure out what size of helix you need to make. But I think at this level, it's just easy enough to just guess and check until you get the largest one you can create. 0.17 didn't work, 0.15 did. So there we go. And so then again, we want to follow that up with a contour. Right click, create derived operation, 2D milling, contour. And all we have to do is hit OK because it keeps everything, keeps the same tool. We can kind of see that it's going to come in, do the lead in, go around, clean up that material. All right, the next thing to look at is look at all these small holes that we're making. And if we inspect, these holes here have a diameter of 0.196. These are going to be smaller because they're tapped. Actually, we don't want the distance between. We're just going to go here. These are 0.156, which is the diameter that we would need to and get those holes before we tap those holes. And I recommend we just use a boring operation with a small tool. We're going to need something smaller than 3/16. So let's do the 1/8 inch end mill, and let's just bore everything with a single operation here. So going here, going to cam, on the drop down, hitting bore. What we want to do is we want to select kind of the entire cylinder like that. We want to get all of these as well. Not just the top like that. You need to basically select the cylindrical face. Okay, so I'm getting all of these. Now you might be wondering, is this going to work because this is at a different depth. Notice the starting height here is lower than the starting height here. But we'll talk about that in a minute. The tool we're going to use is it needs to be smaller than 0.15, and so we're just going to go to the 1/8 inch flat end mill. So this is a pretty small end mill that we have. Okay, and we need to be delicate with it so it doesn't break. But what we can do is go to, so we've selected the tool, we've selected the geometry. On the depth, notice the top height is the whole top. And so notice this starts the helix here, and this one starts the helix at the top of this hole. So that's going to work out fine. Notice the bottom height is the whole bottom, which is right at the surface of the fixture plate. I like to stay a little bit above it, typically between 3 to 5 thousandths. 4 thousandths is about the thickness of a sheet of standard printer paper, and that would just leave a tiny bit of foil at the bottom. And we can clean that up with the deburring tool, and we can not touch or dig into the fixture plate. So that's a good way to do it. Couple of other things that I sometimes like to do is I like to actually start the helix a little bit higher and not just right at the whole top. Maybe like 10 thou higher, just bring that up a little bit. Also, since this is a boring operation with such tiny hole diameters, the one thing, if I can get a better view of the helix is pretty steep, and I like to not go so steep on that helix. And so let's just define the ramp as as a ramp angle instead of a pitch, and like maybe 4 degrees or something. That's still much less of a steep angle coming in, and it's going to take longer, but the tool is going to be a lot safer. And so you can see that we're going to go in and bore all of those holes and clear those out. And we can hit OK. And one thing to be aware of is the order in which we're doing things. Realize if we didn't clear out this counter bore here first, so this counter bore here, before we did this, what would happen is the tool would dive through this 1/8 inch material and just break. That small end mill would break. And so you got to make sure that you're clearing out the material before you do this small bore for this hole. Now you could do the bore first if you change the height. Okay, so notice if we go here on the heights, instead of hole top, you went to model top, you would start boring way at the top, okay, before the counter bore was done. But that's kind of a waste of time. And so, because we're going to clear that out anyway with the adaptive, which is much quicker. So my advice is just stay at hole top, but make sure that you clean out that material, that counter bore first before coming back and cleaning this up. So let's take a look at what's left. We have the counter bores done. We have the holes through. We have these holes done. We have the pockets done. Really all that's left are the bearing holes, and then we need to go around and cut everything out. And so let's take a look at how to do that. Bearing holes is just very much like what we did before. We're going to go to 2D adaptive, and we'll select, I'll just select here and here. The tool that we'll use, these are larger holes, so we can go back to the 1/4 end mill. The other thing that I want to do is on the depth. Since this is at the very bottom, I want to stay above the bottom by 4 thousandths. So I'm not touching the fixture plate. We want to leave radial but not axial, and then go OK. And so there we are. Now these are bearing holes, and if you remember on bearing holes, we want to make them a little bit larger than what they're designed as, because they're designed to be the same diameter as the bearing, but we need to make them a little bit larger to allow for the bearing. And I like to make it, 1/1000th or a little bit more than 1/1000th of an inch larger. And then I, in fact, test them before we pull the part off of the mill to see if it is okay. So what we're going to do is go to create derived operation, do the 2D milling contour, and we're going to do a couple of things. One is everything's the same on the tool, geometry, and depth. However, here for stock to leave, we are going to have a negative stock to leave to make the hole a little bit larger. And as we've done before, I found that 5 10,000ths of an inch, which would make the hole 1/1000th of an inch larger, or 6 10,000ths of an inch, which would make the hole 1.2 thousandths of an inch in diameter larger. Because remember, this is the radius. We'd have to multiply that number by 2 to get the actual diameter increase. One mistake I've seen is people put 6 thousandths instead of 6 10,000ths, and that would be way too large. That would make the hole 12 thousandths of an inch larger in diameter. So it's important that we have the 3 zeros and then the 6, which means that the 6 is in the 10,000th spot. And so that will make the hole diameter 1.2 thousandths of an inch larger. And we found that works pretty well. And then the final thing that I like to do is repeat the finishing pass. So we go around twice. The first time we take out the material, but if there was any tool deflection, it's just going to clean up that on the second pass. So if we just simulate these two, we can kind of see what's happening. So we're coming down, doing the clearing, And I'll just let it play here. It's a little bit disturbing with the flashing there. Hopefully it's not bothering you too much. So as the tool comes around, we are leaving the 4 thousandths of an inch on the bottom. We're leaving 20 thousandths of an inch along the radial. Then we're going to come back and do a contour to clean that up. So we're doing a contour and we do it again. That is called a spring pass. That second pass follows the same exact path as the first pass. It is just ensuring that if there was any tool deflection that we clean up that material. So now our bearing holes are done. What we need to do now is we need to do the perimeter. We need to cut this out. And to cut it out, we're going to do a contour. So we're going to do 2D contour. And you can click the top or the bottom. I'll just click the bottom here. And we'll use the 1/4 inch end mill. The depth, we're going to stay 4 thousandths above. However, this is a 1/4 inch thick. And so what we're going to do is multiple depths. We're going to do multiple depths, and I want to do this in 2 steps. So if this is a 1/4 of an inch, I need the maximum roughing step down to be around an 1/8. So we can maybe do 0.125. I notice it's not quite a 1/4 of an inch because we're staying 4 thousandths of an inch above. Okay. One thing you can do is just to ensure that each step down is the same height. We can just use even step downs. And we're not done, but I'm going to hit OK and let's see what happens. Okay, so you can kind of see we have this lead in. Here's the problem on this. On that lead in, we're diving vertically into material. Not acceptable there. Very hard on the end mill. We will not be doing that. So that's bad. This looks okay here, but I definitely don't like that dive in. So what we're going to do is here under this pass, I'm sorry, it's the last linking tab. There is a ramp feature. And basically, it kind of, the tool doesn't dive, it comes in at some angle. In this case, it's 2 degrees. And you'll be able to see what happens there. Okay, so the tool comes in. You can see in red, it's slowly diving in. So let's take a look there, simulate. So here, it's slowly entering in and it's diving in. That's exactly what we want. And then it goes to an 1/8 of an inch, goes around, and then it dives again with that ramp to the bottom. It goes around, and once it goes around, at the end, we have a problem. You can see here it leaves, and it's actually cutting through full depth as it exits. So I don't like that. So what we're going to do there is get rid of the angle, the sweep angle. We're just going to change to 0. And so notice now it's entering and leaving parallel to the part. A couple other things. This is a slot cut. You might want to slow this down a little bit. I found that this still works a little bit, but it might help if we slowed it down. Typically, I say in a slot cut, half the speed, so we could do that. The other thing that you need to think about is what's going to happen to the part when I get here. There's a good chance it's just going to flip out and fall out. And so might be smart to add a few tabs. I really don't like adding thick tabs because it's messy to clean them up with a deburring tool in a file. And a lot of people have a hard time doing that. But I think tabs are smart. So we can add some tabs. We don't want to add them too thick. I've seen people add a 1/16 of an inch thick tab, and those are really too much. So let's do 3/8 of an inch wide, 0.375, and then let's just say maybe 20 thousandths deep. Okay, and we can order by distance. Maybe we want them every 1.5 inches, and you can kind of see where it's going to put them. It's really only putting 2 there. Maybe we want them every inch. That looks reasonable, that it puts it there. And then we can hit OK. So it's going to leave these tabs. I like to create as small of tabs as possible. I've gotten away, in fact, by leaving no tabs in some cases, and that 4/1000th of an inch that I left was enough to hold it in place. But sometimes the part kind of flips out, and so we'll leave the tabs there. It would be nice if we did a little bit of chamfering and added on the chamfers there to take off the sharp edges. So we'll do that as a last step. And we really need the tabs to hold that part in place, or we won't be able to do any chamfering. So the final thing we're going to do is just 2D contour. Select the top edges here on everything. This takes a minute. The deburring can be done by hand, but it's nice for the machine to do it because it leaves a nice even chamfer there, and we can really get consistent results. And so we can even do the outside perimeter here. So I think I selected everything there. Again, my previous videos on the chamfer, we have a tool, basically the countersink tool that we use for the 82-degree countersink bit, that leaves a nice chamfer, and we have it in the machine. And so we're just going to use that. And so we'll go select. We're going to go the contour. We've already done that. We don't need to really do anything on the depth, but we do need to do something on the chamfer. We found that a 15th thou chamfer is great. You do need a chamfer tip offset. And again, previous videos on this have talked about the chamfer tip offset. You can have a little bit larger than the chamfer width here is fine, but if you get if it doesn't create the chamfer, you will get an error if this number is too big because the chamfer mill isn't that large. And so if you offset it too much, it won't work. But we want to make sure that the tip isn't riding directly on the edge. We want it offset inward a little bit. And so that's all we have to do. And we hit OK. And now we have our chamfers. And let's run through it really quick on the simulate. Not going to sit here and watch everything, but so we'll skip through the sections. There's the contour now, where we're doing the small counterbores for the with the smaller end mill. Now we're cleaning those up with the contour. We go and do the boring for all the holes. Now we're cleaning up doing the bearings, doing the double pass there on the bearings. And then finally, we will do the outside perimeter here. Okay. Oh, I guess that isn't the final. We're going to then do a little chamfer. And you can see the nice little chamfer that it will put there. Okay, so doing the part, that's the part.